Okay, in this lecture we're going to start our Chapter 2 material on applications of integration. And in this first section, 2.1, we're going to talk about finding the area of a region between curves. So recall from the last part of your Calculus 1 course that a definite integral of a function on some interval from a to b represents the area of the region under the graph of that function and above the x-axis on the x interval from a to b. So the problem that we're going to be considering in this section is related. It says, suppose that we have two functions, f and g, which are continuous, and we'll assume that f of x is greater than or equal to g of x for all values of x in the interval from a to b. So geometrically, that means the graph of f of x lies above the graph of g of x on some interval. And the question that we're posing is, what is the area of the region bounded by these curves on the interval from a to b? So let's sketch a visual of what we're asking here. So let's suppose that we're working in maybe the first quadrant of the xy plane. And we have the graphs of two functions. Let's say we have one, which is the graph of a function f of x. And we have some other function, g of x, which are both continuous, so their graphs are these nice smooth curves. And the graph of f of x lies above g of x. That is, f of x is greater than or equal to g of x for all values of x on some interval, let's say from x equals a to x equals b. And the question of interest is, what is the area of this shaded region that lies between those two graphs, f of x and g of x, over this interval from a to b? So here, maybe I'll call my region R, and I want the area of that region. So in order to find this, well, we could make use of what we know about the definite integral of a function as representing the area under the graph of a function. So here, to get the area of the region that we're interested in, I could first take the definite integral from a to b of f of x with respect to x. And geometrically, that would correspond to finding the area under the graph of f of x on the interval from a to b. So we would find the area shaded in red here. Now, we can then subtract the definite integral from a to b of g of x dx, which would be the area under the graph of g of x over that same interval. And so taking the difference of those values, well, what we're left with is the area of this shaded region R that lies between the two curves. That was the region, or the area of the region that we wanted. Now, in order to simplify our formula for area between curves, we can use properties of definite integrals, namely that the integral of a difference of two functions over some common interval can be written as a integral of the difference of the two functions. So that is, we're going to look at the function f of x minus g of x and integrate that difference with respect to x over our interval from a to b. So one way to remember this is you're sort of taking the area under the larger curve or the upper curve and subtracting the area under the smaller curve, and then that gives you the area of the region between those two. So what we have derived is the following theorem, which gives us a formula for the area between curves. So this says, suppose f and g are continuous functions, and f of x is greater than or equal to g of x. So that is, f of x is the upper curve for all values of x on the interval from a to b. So in this case, the area of the region bounded by the curves f of x and g of x from x equals a to x equals b is given by the integral from a to b of the difference of the two functions, f of x minus g of x with respect to x. So now that we have this formula, let's look at a few examples making use of this. So in our first problem, we are asked to find the area of the region bounded by the graphs of f of x, which is 1 over x, and g of x, which is 1 over x squared, on the interval from 1 to 2. Okay, so I'll mention for the examples, or for the problems in chapter 2, it's often helpful to sketch the graphs of the functions and visualize the region that we're interested in. We'll see that not only for problems in section 2.1, but throughout this chapter 2 material. So my first step is going to be to graph or give a rough sketch of the graph of these two functions over my interval of interest. So let's start with the first curve, the graph of y equals f of x, which is 1 over x. So we know that the graph of 1 over x is this hyperbola sort of shape. I'm only interested in the interval from 1 to 2 here, so I'm only going to draw the part that lies in the first quadrant. So this is our curve y equals 1 over x. And our other function, g of x, which is 1 over x squared, looks similar to the graph of 1 over x. It looks something like this, where these two curves, 1 over x and 1 over x squared, both pass through the point 1, 1. So they're intersecting at that point. And then we're looking for the area of the region between these two curves on the x interval from 1 up to 2. So to draw our region of interest, we would have this little sliver shaded in black. So to find the area of that region, we would integrate over the specified interval, in this case from 1 to 2, and the function that we're integrating is going to be the upper curve minus the lower curve. So remember here, our upper curve on the interval from 1 to 2 is the curve in blue here. We can see from our graph that from 1 to 2, 1 over x squared is or actually I've got these backwards. So let me change my notation here. On the interval from 1 to 2, 1 over x squared is smaller than 1 over x. So let me just change the labels on my graphs here. Now, how can we determine that 1 over x is larger on that interval? Well, we can choose some value of x within our interval. Let's say maybe 1.5 or 3 halves. And we know that 1 over that x value, in this case maybe 3 halves, would be 2/3. Now, taking that value and plugging into our other function, 1 over x squared, well, we would have 1 over 9/4 or 4/9, which is certainly less than 2/3. So to determine which curve is your upper curve, you can always choose a test value of x within the interval of interest, plug that x value into each function, and see which gives you the larger value. So here, the upper curve is the curve shown in blue, which is 1 over x. And then we are subtracting the lower curve, which was 1 over x squared. And then integrating with respect to x. So in order to integrate this, we might prefer to rewrite the second term as x to the negative 2 power instead of 1 over x squared. And now we can integrate each term. We know the antiderivative of 1 over x is given by the natural log of absolute value x, and we are then subtracting the antiderivative of x to the negative 2, which would be x to the negative 1, and then we're dividing by negative 1. So here, since we're subtracting that negative, this will become addition. And then for our antiderivative, we are evaluating from 1 to 2. So rewriting this just a little bit before we substitute in, we have the natural log of absolute value x plus x to the negative first, which is the same as 1 over x from 1 to 2. So we start by substituting in our upper limit of integration, which was 2. So we're going to have the natural log of 2 plus 1/2. And then we subtract the value that we get by plugging in 1 for x. So we would have natural log of 1, which is simply 0. So this term is 0. And then plus 1 over 1, which is 1. So simplifying just a little bit, we have the natural log of 2, and then I had a plus 1/2, and I'm subtracting 1, which leaves me with a negative 1/2. So this value, natural log of 2 minus 1/2, would be the area of the region shown shaded in black here. All right. So let's look at some other examples. So here, I'll mention in most of these problems, or in some cases, we want to define the interval of interest based on where the graphs of these two functions intersect. So often we are not given the interval of integration for a problem, but we need to determine the interval based off where these two graphs intersect one another. So some examples we'll look at, this next one, is to find the area of the region bounded by the graphs of f of x, which is x squared minus 4x, and g of x, which is 2x. So as I mentioned in that first example, we often want to sketch the graph of the given functions, and in order to sketch the graphs of these functions, we might need to determine the points at which they intersect. So in order to determine our points of intersection, we would set our two functions equal to one another. So that is x squared minus 4x, we would set equal to 2x. And we find, if we move all of our variables to the left-hand side of the equation, that x squared minus 6x has to be 0. And so I can then factor this as x times x minus 6 is 0. So it follows that either x is 0 or 6. So these are the x values for our points of intersection. So using this, let's see if we can sketch the graphs of these two functions and visualize the region that we're trying to find the area of. So we know that these two curves intersect when x is 0. Now what is the y value for those points of intersection? Well, we can find the y value by substituting x equals 0 into either function. So substituting into f of x or g of x, we find that the corresponding y value is 0. So both of these curves are passing through the origin. Now the other point of intersection is when x is equal to 6. To find the y value, we could substitute 6 into either of our functions, f of x or g of x, and we get a y value of 12. So to draw this a little more to scale, let me maybe make this 6. The corresponding y value we see would be 12. So they're also going to both pass through this point. So to sketch our two functions, well, let's start with this first one, f of x. So f of x here is a quadratic with a positive x squared coefficient. So we know that the graph of a quadratic is a parabola. Since the coefficient for x squared is positive, it's opening upward. So I don't know precisely what this graph looks like, but it's a parabola opening upward and passing through the 2 points of intersection that we found. And our second function, g of x, which is 2x, well, that would have a graph which is a line of slope 2 and passing through the points of intersection that we found. So our region of interest is the region between those two graphs. Okay. So we can see here, of course, that on this interval, y equals 2x is the upper curve, and y equals x squared minus 4x is the lower curve. So using our new theorem, we can find the area of this region by integrating over the given interval, which in this case we found the x values for our points of intersection were 0 and 6. So we're integrating over that interval from 0 to 6. And the function that we're integrating is our upper curve, which was 2x, minus the lower curve, which was x squared minus 4x. And we have to remember here that we're subtracting this entire quantity, x squared minus 4x. So the negative's going to distribute there since we're subtracting that entire quantity. Now before I find my antiderivative, I'm going to simplify the integrand a little bit by grouping like terms. So let's see, here we had a 2x, and then I was subtracting a negative 4x. So that's same as adding 4x. So altogether we have 6x, and then minus the x squared term. We're then integrating with respect to x. So here, finding our antiderivative, we would have a 3x squared minus the antiderivative of x squared is 1/3 x cubed, which we're then evaluating from 0 to 6. So substituting in 6, let's see what we have. We would have a 3 times 6 squared, which is 36, minus a 1/3 times 6 cubed. So let's think about it like this in order to make our algebra a little easier. 6 cubed would be the same as 6 squared, or 36, and then times 6 again. So let's think about why I wrote it like this. Well, our first factor was 3 times 36, and then I'm subtracting. Well, when I have my 1/3 times 6, that gives me 2, and then I'm multiplying by 36. So I've got 2 times 36. And we can see pretty quickly here what we're left with. Well, 3 times 36 minus 2 times 36 is 1 times 36. So the area of that shaded region is 36 square units. Now in this problem, we're not given the unit for measurement, if this is like inches, feet, yards, miles. So we would just have to say square units in this case. So let's look at another one of these where we're considering a region bounded by two curves, so that we need to find their points of intersection. So in the next example, we're asked for the area of the region bounded by 4x squared and x squared plus 3. So again, in order to determine the interval over which we're going to integrate, we need to find the points where these two curves intersect, which we can do by setting these functions equal to one another. So that is 4x squared will be equal to x squared plus 3. And we find by moving all of our expressions to one side of the equation, maybe the left-hand side, that 3x squared minus 3 is equal to 0. So I can then divide this equation through by 3, and I have x squared minus 1 is 0. And then this factors as x plus 1 times x minus 1 is 0. So it follows that x could be positive or negative 1. All right. So let's see if we can sketch our graphs of these functions and determine the interval that or determine our region of interest. So here in the xy plane, well, we know that these two curves intersect when x is equal to negative 1 or positive 1. So let's look at the graphs of these functions. Our first one, f of x, is 4x squared. So when x is positive or negative 1, the corresponding y value will be 4. And we know that the graph of this function, 4x squared, well, it is a quadratic with the positive x squared coefficient, so it is a parabola opening upward. Here are vertexes at the origin. And it's passing through those 2 points, plus or minus 1, 4. Now our second function, g of x, is x squared plus 3, which again is the graph of, its graph is a parabola opening upward, and that plus 3 term means that our our y-intercept would be at 3. So we have a parabola opening upward. We know it has to pass through the 2 points of intersection that we found, plus minus 1 and 4. So here, labeling these, our lower curve is the 4x squared, and the upper curve is the x squared plus 3. So the region of interest would be the shaded region shown here. All right, so let's find the area of this region. So here, our area would be found by integrating over the interval from -1 to 1. We can see that from our sketch of these curves here. Those were the x values for which these curves intersected. And we would take the upper curve, which was x squared plus 3, and subtract the lower curve, which was given by 4x squared, and we're integrating with respect to x. Now, what we have here is the integral from -1 to 1 of, grouping the x squared terms, we have 3 minus 3x squared dx. And so we can integrate from here. Now, one thing I'll mention before I proceed, and I'll point this out in this example because it's a technique we'll use fairly often throughout the semester, is that we can use the symmetry of our region in order to simplify our work a little bit. So I know from here, I would need to find my antiderivative and then evaluate it at the endpoints -1 and +1. But to make my work a little bit easier, another approach here is to use the symmetry of this region about the y-axis. So let's say that we would find the area just from 0 to 1 between those two curves. So the area that I'm shading in here. Now I know that by the symmetry of this region, that the area from -1 to 0 would be the same as that right-hand portion from 0 to 1. So to simplify, I can make use of symmetry. So let me say by symmetry of this region, I could take the area as the area from just 0 to 1 of the same function, 3 minus 3x squared dx, and then double that value by multiplying by that integral by 2 out in front. So how does this help us? Well, now one of my limits of integration is 0 instead of -1, and generally it's easier to evaluate a function at 0. Plugging in 0 is easier than plugging in -1. So let's see what we have. We have a constant of 2 out in front, and then the antiderivative of this function would be 3x minus x cubed, which we then evaluate from 0 to 1. So we have now a 2 times, when we substitute 1 in for x, we have 3 minus 1 cubed, which is 1. And then we subtract the value that we get by plugging in 0 for x. But we see when we plug in 0, we have 0. So we're left with 2 times 2, or 4 square units for the area of that region. So this last example illustrating that if we have a region which is symmetric about some line, we can maybe just integrate over half of our interval and then double the area that we found in order to get the area of that full region. Now, in the next part of this section, we'll take a look at finding the areas of regions between the graphs of functions that may intersect at multiple points over some interval, and maybe the same curve is not always the top curve within our interval. Maybe over some subinterval, one curve is the upper curve, and then maybe it crosses the other one, and becomes the lower curve on some subinterval. So I'll mention here in what we have been looking at so far, we required f of x to be greater than or equal to g of x. So that is one of the curves was the upper curve over the entire interval of interest. But what if we want to look at regions bounded by the graphs of functions that cross one another within a given interval? So let's take a look at this graphically. So here, let's suppose that we have in the first quadrant of the xy plane the graphs of two functions. Let's say y equals f of x, and we have the graph of some other function shown here. Let's say y equals g of x. And we're looking for the area of the region bounded by those two curves on some x interval, let's say from A up to B. So I'm looking for the area between those curves. On this interval. Now we can see from the way that we've drawn our curves that these two graphs intersect one another throughout this interval, and the upper curve changes. So let's label our points of intersection here. Maybe we have from A up to let's call this point C. And we see on that interval from A to C, the red curve, or f of x, is on top of g of x. Now, these curves also intersect at another x value. Let me maybe call this D. And we see that on the interval from C to D, now the graph of g of x, or the blue curve, is the upper curve. And then finally, on my interval from D to B, we see that the red curve again crosses over the blue curve and becomes the upper curve. So how are we going to find the area of this shaded region? Because our formula was dependent on one of the curves being the upper curve over our entire interval. So the way that we can do this is by breaking up our interval into small subintervals. We're going to use that property of the definite integral that we can split it up. So in other words, to get the area of this first little shaded region, we are going to integrate from A to C the upper curve, which is f of x on that interval, minus the lower curve, g of x, dx. Then to find the area of this next shaded region, where g of x is the upper curve, we would integrate from C to D the upper curve, which was g of x, minus the lower curve, f of x on that interval, dx. And then to get the area of this final little shaded region, where f of x again crosses to be the upper curve, we would integrate over that last interval from D to B, the upper curve f of x minus the lower curve g of x with respect to x. Or another way to write this sort of formula more succinctly, but which still requires us to split the interval, we could say take the interval from A to B of the absolute value of f of x minus g of x. And including this absolute value in our integrand will automatically give us the area between the graphs of f of x and g of x, regardless of which curve is on top. However, in practice, if we're trying to find an antiderivative of the absolute value of a difference of functions, well, we would have to split that integral up over these smaller subintervals, depending on which function is the upper or lower function. So it's just a more succinct way to write that formula. So let's look at some examples of this. In our first example, we are asked to find the area of the region bounded by the curves y equals x squared plus 1, y equals 3 minus x squared, and the vertical lines x equals negative 2 and positive 2. So as with our earlier examples, let's see if we can sketch these curves. And we want to start by looking for points of intersection. Now, to find the points of intersection, we would set these two functions equal to one another. That is, x squared plus 1 will equal 3 minus x squared. And moving all of our variables to one side of the equation, we would have a 2x squared minus 2 is equal to 0. I can then divide through by 2, and I would have x squared minus 1 is 0, and it follows that x could be positive or negative 1. So let's see if we can sketch our region here. So here in the xy plane, we have two functions. The first one is x squared plus 1, shown here. So we know that the graph of that is a parabola opening upward whose vertex is at 1. And we know that these two curves were intersecting at the x values -1 and +1. Now the corresponding y value you can find by substituting x equals ±1 into either function. And we find that the corresponding y value is 2. So our first curve passes through those 2 points. It is this upward opening parabola whose vertex is at 0, 1. Now our second curve, or our second function, is 3 minus x squared. So the graph of that would be a downward opening parabola whose vertex is at +3. Now this parabola opens downward. Of course, it must pass through those same points of intersection which we found. So it looks something like this. And then let me sketch in the rest of, or a little more of the first parabola. So here, the one shown in red is x squared plus 1. The one shown in blue is our 3 minus x squared. So we see that there is some region which lies between those two curves. But remember here that we were also told that we wanted the region not just bounded by those two curves, but also the curves x equal -2 and +2, which would be vertical lines passing through x equals +2 and x equals -2. So here, extending my curves a little bit to visualize our region. We also want to account for the region shaded here. All right. So in order to find this region, we can split up our integral into 3 pieces. So we could first integrate from -2 to -1, where the red curve is the upper curve. And then we would integrate from -1 to +1, where the blue curve is the upper curve. And then we would integrate from 1 to 2, where the red curve again crosses and is the upper curve. Or, in order to simplify our work a little bit, we can again make use of the symmetry of this region, as we did in that last example. So it's not too difficult to see here, even though this is not drawn to scale, that the area from 0 up to 2, so that is if I find the area shaded in red here, I would have the same as the area from -2 up to 0. So I could just double that, and then I only have 2 integrals to evaluate instead of 3. So let's take a look at this. I'll say by using symmetry, I could calculate the area of this region by taking twice the area of the region which I've shaded in red. Now to do that, I would first need to integrate on the interval from 0 to 1, where the blue curve is the upper curve. So I'm taking there 3 minus x squared, which is my upper curve, minus the lower curve, x squared plus 1, with respect to x. And then I would need to add the integral from 1 to 2, where the red curve is the upper curve, that is x squared plus 1, and I'm subtracting my lower curve, which was 3 minus x squared dx. So let's see what we have here. So we have our constant 2 out in front. For my first integral, we have the interval from 0 to 1. And grouping some like terms, let's see what we have. So we have a 3 minus 1, which gives us 2. And then I had a negative x squared minus another x squared, gives me negative 2x squared dx. And then the integral from 1 to 2, grouping our like terms here, we would have x squared minus a negative x squared is 2x squared. And then plus 1 minus 3 gives us negative 2. We're integrating with respect to x and then doubling that entire value. So let's evaluate each of these integrals. We have 2 times the antiderivative of this first function would be 2x minus 2/3 x cubed, which is evaluated from 0 to 1. And then we are adding the antiderivative of this function is a 2/3 x cubed minus 2x, which we evaluate from 1 to 2. So what we're left with is a constant 2 times, for our first antiderivative, we start by substituting in 1, and we would have 2 minus 2/3. Then we subtract what we get when we substitute in 0, but we see that by plugging in 0 for x here, we have 0. Then we are adding for our second antiderivative. We start by substituting in 2. So let's see, 2/3 times 2 cubed, which is 8, gives us a total of 16/3. Minus 2 times 2 is 4. Then we subtract what we get when we substitute in 1 for x, which we see would be a 2/3 minus 2. So in our last step, we can simplify and collect like terms. So let's see what we're left with. We have a 2 times, grouping our integer terms or whole number terms. I have 2 plus a negative 4 would be negative 2, and then I'm subtracting a negative 2 or adding 2. So all of those integer terms cancel. Our 2 minus the negative 2 is 4, or then subtracting 4. And then grouping our factors, which involve a common denominator of 3, well, I have a 16/3 minus 2/3 minus another 2/3 gives us 12/3 or 4. So finally I have 2 times 4 would be 8 square units for the area of that region bounded by these the graphs of these two functions and the two vertical lines, x equals -2 and +2. Okay, so in our last example for this lecture, we will consider the following. We are asked to find the area of the region bounded by the graphs of f of x, which is sine x, and g of x, which is cosine x, on the interval from 0 to pi. So again, in order to visualize our region, or determine whether these curves cross one another within that specified interval from 0 to pi, it's helpful to graph these. And we would start by looking for points of intersection of these two functions. So here we would find those by setting the functions equal to each other. That is, let sine of x equal to cosine of x. And it's not quite as simple to determine our values of x here. So perhaps if you are very familiar with the unit circle, you know the values of x immediately, for which sine and cosine are equal to another. But if not, we could solve algebraically, by maybe grouping our trig functions together as a quotient, sine x, and if I divide both sides by cosine x, I have sine x over cosine x is 1. However, we know that the ratio of sine x divided by cosine of x is the same as tangent of x, which has to equal 1, and taking the arctangent of both sides, x is arctangent of 1, or pi over 4 radians. So let's think about sketching our region of interest. We're interested in these functions on the interval from 0 up to pi. So starting at x equals 0, moving up to x equals pi. So let's start with the graph of f of x, or sine of x, first. Now sine of 0 is 0. And then, let's see, we were told that these curves intersect at pi over 4, so let me maybe draw my interval first. Here we're going all the way from 0 to pi. Of course, half of that is pi over 2. Half of that would give us our pi over 4, or a 3 pi over 4. So sketching our sine function, f of x equals sine x, well, we have at 0 a value of 0. And then the sine function is increasing from 0 to pi over 2, where we have a y value of 1. And then it starts to decrease, and sine of pi is 0. So this would be our sine x function. And the cosine function we'll sketch in red. Now cosine of 0 is 1, so we start here. And initially, cosine of x decreases to a value of 0 at pi over 2, and then continues to decrease down to negative 1 at x equals pi. So this is our cosine x function. So we see, of course, that these two curves cross when x is equal to pi over 4. So the area that we're, or the region that we're interested in, is the region between those two curves from x equals 0 up to x equals pi. So the region shown here. And because these curves cross one another on that interval, we're going to have to split up this integral into two pieces, depending on which curve is the upper curve. So let's start on the interval from 0 to the point of intersection, pi over 4. We can see from our graph that cosine of x is the upper curve. So we would have cosine of x minus the lower curve, which was sine x dx. And then we would add the remainder of our region. That is the integral from pi over 4 up to pi, where we see our blue curve, or sine x, is the upper curve. So we would have a sine x minus cosine x dx. All right. So evaluating this first integral, we need to find an antiderivative. So the antiderivative of cosine x is sine x, and then we're subtracting the antiderivative of sine x, which is negative cosine, but since we're subtracting that value, we have a positive cosine x evaluated from 0 to pi over 4. Then we are adding, for the second integral, the antiderivative of sine x, which is negative cosine x, minus the antiderivative of cosine x, which is sine x. And this we are evaluating from pi over 4 to pi. So let's see what we have. Evaluating the first antiderivative at our upper limit, pi over 4, Well, we would have sine of pi over 4, which is the square root of 2 over 2, plus cosine of pi over 4, which is also root 2 over 2. Since pi over 4 was the value where sine x and cosine of x crossed one another. They have the same value at that x value. Then we subtract what we get when we substitute in 0 for x. So plugging in 0 for x here, we have sine of 0, which is 0, plus cosine of 0, which is 1. Now for our second piece, we first evaluate at pi. So let's see what we have. Substituting in pi, we would have cosine of pi is -1, but since it's got the negative out in front, we have 1, minus sine of pi, which is 0, and then we're subtracting the value we get when we substitute in pi over 4. So here, cosine of pi over 4 is root 2 over 2. We had a negative out in front. And then minus sine of pi over 4 is also root 2 over 2. So let's see what we're left with. Grouping these first two terms, root 2 over 2 plus root 2 over 2, gives us 1 root 2. We're then subtracting 1 and adding 1, so those terms will cancel one another. And on the end, we're subtracting the quantity, negative root 2 over 2 minus root 2 over 2, which becomes addition of a 1 times root 2. So altogether, we're left with 2 times the square root of 2 for the area of the region between those curves on this interval from 0 to pi.